Okay, so I will try to show what has been done so far in the framework of the SWARM mission, mostly with some additional data from platform magnetometers from Cryosat in terms of 3D mantle conductivity. And basically the questions how to use MSS data for these studies were already discussed by Niels and Anya with these beautiful animations showing the advantages of having large or very fast local time coverage by this in-kind trajectory. So this presentation will have two parts. First, I will speak about tidal magnetic signals and how to try to invert them in terms of suboceanic upper mantle conductivity. And then I will look at the magnetospheric variations and the deeper, let's say, lower mantle conductivity. So why is it an important parameter for us geophysicists? Of course, the conductivity is tied to the thermal and compositional and mineralogical state of the mantle. In the upper mantle, we can mostly ask about the melt and water content. These are the main governing parameters for the upper mantle conductivity. When we get lower, we could try to look for the effects of, for example, spin transitions or post-perovskite or the large low shear velocity provinces in the lower mantle. So let's start with the upper mantle. In this case, we have the lunisolar tidal forcing, which generates periodic flows in the Earth's oceans. These are just two-dimensional flows. That means the velocities are same across the depth of the oceans. And we split them with some approximations to individual frequencies like the semi-diurnal, diurnal, and so on. These flows generate the main field and generate signals which penetrate into the upper mantle. And it has been shown that they are sensitive to the upper mantle conductivity. A couple of years ago, Alexander Greiver used them to constrain the 1D conductivity profile across the lithosphere-asthenosphere boundary to detect basically a jump in the conductivities. And we are trying to take the next step and trying to apply them for a 3D inversion for the upper mantle conductivity. So we are relying basically on the data processing by other groups. One of them is the DTU space group, and there have been increasing number of versions of these products. MTI now currently is the generation 9 version. And they are able to detect the M2 and now also the N2 fields using, for example, the east-west and north-south gradients of magnetic field in the comprehensive inversion. A second approach, which is based more on a very strict selection of data, was presented by Alexander Greiver. And he is just trying to use dedicated inversion for the residua after subtracting the main field and other field model, also using the gradients. And he was able to recover not only M2, but also N2 and O1 tidal signals. In order to model to solve the problem, we need to solve the 3D EM induction equation. So for a given conductivity model and given forcing described by this velocity field U and main field model BM, we find the induced magnetic field, and then we of course try to formulate the inverse problem to try to fit the magnetic field by changing the conductivity structure. And what you need is a good model of the source field. That means a good model of the ocean flows. For this, we use the TPXO satellite altimetry assimilated ocean flow models for the individual tidal constituents. And you also need a decent model of the seawater conductivity. We use a 3D model now currently based on the World Ocean Atlas, and we have plans to some upgrades of these settings in our future modeling. We also use some 3D map of the ocean bottom sediments using different thicknesses of these sediments and assign a priori conductivities. This is again something that is being developed and will be soon upgraded. We also have some independent information on geomagnetic observation in terms of this winter sea class of models, which are generated for the upper mantle from seismic tomography and also thermal flow and gravity fields. And they have been converted to conductivity using laboratory measurements and some averaging rules for conductivities of different mixtures, including not completely self-consistent, but still at least some formulation for water presence and melt presence. And we can use this kind of model first in our numerical scheme to do some corrections. Basically, we are not able to run the inverse problem at the full numerical resolution. So we try to pre-correct the data by using high resolution runs with this a priori model, and then we can lower our resolution in the inverse modeling. And second use for this model is actually to try to use it as a regularization. So try to ask the question, how much we need to change this model, mostly by including some water and melt, to improve our fit into the data. Because the actual fit of this model into the tidal magnetic data is reasonably good. For the inversion, our unknown domain is only under the oceans. We don't try to invert below the continents. And we use relatively coarse parameterizations for the mantle conductivity in something like 13 layers in the upper mantle, and the grid size, depending on the spherical harmonic degree of individual tidal components, can be 4 to 10 degrees size. This leads to problems, inverse problems with tens to hundreds of thousands of unknown parameters in terms of log conductivity. Then we try to minimize really the fit in terms of magnetic field, the observed field from the analysis of swarm data and the predicted by the forward modeling. And we choose the optimal regularization by just looking at the L curve and trying to find some optimal trade-off between data fit and regularization. So here are some results. In the left column, you can see the electrical conductivity in different layers for the a priori model, for the VDMX model, and then a result of a smooth inversion for these two data sets, the driver-Olsen and the comprehensive inversion data set. And by smoothing, I mean we try to constrain the horizontal gradients of log conductivity in each layer. So you can see that there are significant differences between these two data sets, especially at these lower depths. When you get slightly deeper, it's a little bit improved, but still there are significant differences. If we try a different inversion where we try to use this winter CE as a priori model and try to regularize towards this model, the agreement between these two data sets is slightly better. And you can see in some places mostly increased conductivity compared to the a priori model, which might signify increased presence of melt or water in the mantle. So to conclude this part, we have demonstrated in a separate paper that on synthetic data this works quite nice, but of course synthetic data are not real data. And definitely the most limiting is not the methodology, but the data sets. And we need more data, we need better models, and we need to get closer the results of the different analysis techniques used to process the data. We are also trying some preliminary runs, including also the N2 and O1 tides. And regarding then the backpropagation to the geophysical winter CG model, it's not very likely to be able to run a full coupled inversion, but we might feed back the information on the water and melt content into this model. And of course, MSS1 would be a great help, as will be probably in the future also nanomaxat and possible other missions, because it will improve the coverage in the low to mid latitudes. It will improve the coverage in local times, and it will improve significantly the other non-tidal models, non-ocean models, especially the ionosphere, which will help us to still better recover the ocean-induced magnetic field. The second topic I'm interested in is looking at the deep mantle conductivity mostly in the lower mantle, using the changes of the magnetospheric field, the time variation of the magnetospheric field. The forward problem is now cast in the time domain, not in the frequency domain. And basically what you need is as good as it's possible a model of the external field coefficients and of course of the induced field coefficients. And then by forward modeling, given the loading by the external field, we predict the internal field and define our misfit as a goodness of fit of the internal field from the forward problem with respect to the data. Of course, with some possible weighting and regularization. And currently, the data are basically limited. There are different versions of these products, but mostly the external field is known up to degree 3 and order 1, with time sampling from 1.5 hours to something like 6 hours for the higher harmonics. And for the internal field, the standards models derived by Lars Tefner-Clausen are degree and order 3 in some versions with the addition of 4.1 and 5.0. And again, with this about 6-hour sampling for the higher harmonics. And these models are derived using all swarm data, but also the Cryosat-2 platform data and the ground observatory data. And there is some downweighting in the processing in the polar areas due to polar electrojets and FACs. We have now a new methodology to improve this processing, but I'm not showing the results yet. It's not yet working fully for long time series. We just have some few small examples. And here are the results from 8 years, so from generation 8 of these external and internal field products. And you can see a regularized, again, with horizontal smoothing model, starting from the upper mantle, going basically through the all mantle. Just for comparison, I'm showing this classification of LLSVP provinces in the lower mantle from paper by Lekic. So of course, you might speculate that we can due to the presence of melt assign higher conductivities to these provinces. So this is just a speculation. What I like very much is this figure where you actually show the Hessian of the data misfit as a function of all parameters. So both in the column and in the row, basically as you progress with these boxes, you are going deep and deep. So from the surface down to the CMB, both on the horizontal vertical axis. And inside each of these boxes are the individual spherical harmonics for the conductivity or log conductivity. And these larger values of this SCN starting basically at the top of the lower mantle at these 670 kilometers down to something like 1800 kilometers. So this is the area where we have significant sensitivity of the data to the conductivity variations. This is our focus. It will be much more difficult to get really down to the D double prime or just above the CMB to see the details. That sensitivity is decreasing. So definitely the magnetospheric field variations are able to probe the conductivity of the deep mantle. I think now it's also on these large scales doable in 3D. And MSS1 will be crucial, especially thanks to this improved local time coverage to increase this spherical harmonic degree of the analysis of the external internal field. Because we are working in the spatial temporal bands when you need resolutions in terms of spherical harmonics, ideal up to degree 5, 6, maybe 10, with time sampling of hours, 1 hour, 2 hours, maybe 4 hours. And this is impossible to do just with swarm. You need more satellites at the same time. Thank you very much.